All right, welcome to the Explainer. Today we're tackling something that makes even the best engineers sweat a little, LeetCode's hardest problems. But what if I told you it's not about being a genius? What if there's a system to the madness? Let's get into it.
I want you to think about this for a second. What if the whole idea of a hard problem is just a myth? Seriously, what if these problems aren't about some random flash of genius, but something you can actually learn? Something systematic? Because that's really the secret we're unpacking today. The key to cracking these impossible-seeming problems isn't some next-level intellect. It's pattern recognition. It's all about learning to see the hidden blueprints that these complex problems are built from.
All right, section 1, the myth of hard. So let's just bust this myth right now. These problems, they almost never ask you to invent some brand new world-changing algorithm on the spot. No way. Think of them more like really well-made puzzles. They're designed to test how you combine the fundamentals in clever new ways. So what actually makes a problem hard? Well, it's kind of like a recipe. It's a mix of a few key ingredients. You might have to combine dynamic programming with some graph theory. You'll definitely have to navigate a tricky state space and be super precise with all those annoying edge cases. See? It's not about invention. It's about a deep, rigorous application of the stuff you're supposed to already know. Okay, so if these problems are just combinations of core ideas, then we should be able to map them out, right? And that's exactly what we're going to do in section 2. We're going to create a map for this territory. We're turning what feels like a chaotic jungle of problems into an organized chart with just 15 core patterns. And here it is. This is our map. Now look, don't even try to memorize all of this right now. That's not the point. The point is to just grasp the big idea. So, for example, look at burst balloons. That sounds like a game, right? And then look at regular expression matching, a totally different text parsing thing. On the surface, they have nothing in common, but underneath, they both run on the exact same engine, dynamic programming. That's the secret. Every hard problem is basically a challenge to find that hidden pattern. Okay, section 3. Now that we have the map, let's zoom in and explore a few of the most important landmarks. We're going to deep dive into a couple of these cornerstone patterns so you can see exactly how they work and, more importantly, why they're so powerful. First up, a real classic, sliding window maximum. The problem itself sounds pretty simple, right? Just find the biggest number in every moving window of a certain size as it slides across an array. The real challenge, though, doing it fast. The obvious brute force way is just way too slow. And that leads us to a really clever data structure. And the best way to understand the solution comes from this amazing quote from our source material. Imagine a queue that refuses to keep smaller numbers behind a larger one. That's a monotonic deck. It's basically a special kind of queue that's a little picky. If a new, bigger number shows up, it just kicks out all the smaller folks that came before it. It's a simple rule, but the effect it has on performance is huge. So let's walk through how this thing actually works, step by step. First off, we're smart about it. We store the indexes of the numbers, not the numbers themselves. This helps us track how old an element is. Now, before we add a new element's index, we look at the back of the line and kick out anybody who is smaller. Then we check the front of the line and get rid of anyone who's fallen out of our current window. And what's the result of all this? The index at the very front of our deque at all times is the maximum value in the current window. It's just so elegant and efficient. Now, you might be thinking, hey, why not just use a heap? A priority queue could do this, right? And yeah, you could, but it would be slower. A heap is going to cost you O of n log k time, because you're paying that little sorting penalty for every element. The magic of the monotonic deques is that each number's index gets pushed on and popped off exactly once. That averages out to an amazing O of n, or linear time. For this pattern, the deque is without a doubt the best tool for the job. All right, pattern number 2. Let's talk about burst balloons. This one has a reputation for being a seriously tough dynamic programming problem. The setup is, you've got these balloons with numbers, and you get points for bursting them based on their neighbors' values. Your job? Get the highest score possible. And this is where the big, counterintuitive insight comes in. This is the aha moment that cracks the whole thing open. If you try to figure out which balloon to burst first, your subproblems get all tangled up because the neighbors keep changing. But, and this is the genius part, if you flip the question on its head and ask, which balloon in this range should I burst last, everything clicks into place. The neighbors suddenly become fixed boundaries, and you're led with 2 perfectly clean, independent subproblems to solve. This reverse thinking is what leads us straight to the interval DP solution. So first we pad the array with ones on each end to act as our fixed walls. Then we define our state, DP left-right, as the max coins you can possibly get from all the balloons between left and right. Then, for that interval, we just try out every single balloon K as the potential last one to be burst. The final score is simple. It's the score from the left part, plus the score from the right part, plus the points you get from finally popping balloon K itself.
Okay, section 4. It's really easy to look at all this and think, okay, cool, but these are just interview puzzles. And that would be a huge mistake. These patterns aren't just abstract brain teasers. They are the actual building blocks of high-performance systems that are running in production right now. This stuff matters way beyond a whiteboard interview.
I mean, think about it. That monotonic DQ we just spent all that time on, it's the engine behind real-time monitoring systems, finding the max value in a fire hose of data. Interval DP, that's a core concept in compiler optimization. And that binary search on the answer pattern, it's used all over the place to solve super complex resource allocation problems. So learning to see these patterns isn't just about passing an interview. It's about becoming a more effective engineer. So for our final section, the big question. How do you actually get started? How do you take all of this theory and turn it into a real skill? Let's lay out a super simple, actionable plan you can start today. And trust me, it's easier than you think. Just start with 2. That's it. Don't try to boil the ocean and learn all 15 at once. That's a recipe for burnout. Pick 2 of these cornerstone patterns and just go deep. Real mastery always starts with focus. So here's your practice checklist. It's 3 simple steps. First, implement the 2 problems we just went over, sliding window maximum and burst balloons, from memory, no peeking at the solution. Second, explain the logic out loud to yourself, your cat, whoever. Can you actually articulate why the DQ has that amazing amortized time? Can you explain the last to burst trick? This really cements it in your brain. And finally, drill the edge cases. What happens with an empty array? What about duplicates? This is what separates a decent solution from a truly great one. And that really brings us to the end. We've deconstructed the myth of hard problems. We've seen that these scary, intimidating challenges are really just built on a foundation of patterns that you can recognize and learn. So the only question left for you is, which pattern are you going to master first?